So hi everyone, this is track number 3 of ElixirConf 2020, and here with us is Jeff Otter. He's presenting us his talk, Debugging Line System on the Beam. Welcome, Jeff.
Hi there. Hey, thanks everybody for coming. Like you said, I'm going to be talking about debugging live systems on the Beam. And my name is Jeff Otter. I used to play the double bass in another lifetime, and I still do from time to time. I live in Topeka, Kansas, and I work for Bleacher Report. I also want to take a second to introduce you to my new daughter, Olive. She's about 5 weeks old now. And I just mentioned that because she might chime in the background, or you might notice me bouncing up and down while I'm talking. That's apparently a new skill that I can't help. Okay, so debugging live systems. What are we talking about when we say debugging live systems, right? I'm not talking about tracing or monitoring or step debugging. What I'm talking about is kind of your last resort for troubleshooting production issues. So let's give a scenario, a problem scenario where this type of debugging can be really useful. Like I mentioned, I work at Bleacher Report. When I started at Bleacher Report, I started on a team that was building out a new feature, like a live chat feature, a direct message type feature. Now, Elixir and Phoenix channels are perfect for this kind of problem, right? That's what it's built for. There's an important feature as part of this feature that if you don't have the chat open right at that moment, right? If you've closed the chat or you've backgrounded the app or whatever, and someone sends you a message, you want to get a push notification that says, hey, someone sent you a message, you missed this important thing. And we were about ready to launch, feature's going great. And then my boss messages me, he says, hello, Jeff, what's happening? And for some reason, he wasn't getting those push notifications. If he didn't have the chat open, he had no idea that there was a conversation happening in the background for him. Now, first line of defense, we have pretty good tracing for all of our apps. So you turn to the tracing and you look at the traces, and sometimes the error is obvious. You get a trace like this. There's nice spans highlighted in red. It shows you where the problem is. It shows you what else happened around the problem, and you get a nice trace. It shows you where the problem is. However, sometimes tracing isn't so helpful. There's no error anywhere to be found. You get traces like this. Other than this particular trace taking like 4 seconds, which that might be a problem in itself, but there's no error. It doesn't tell you what went wrong. And as far as the trace is concerned, everything's great. And this might be, there's no error raised, right? There's maybe a bug in your logic or something like that, but tracing, logging isn't going to tell you that. So this is where we turn to remote debugging. The Beam has a bunch of tools built into this, and for this, the first step, which we're going to kind of gloss over, is getting a remote console. And the reason we're going to gloss over that is because it can vary a lot depending on how you run your application. It's different to get a remote console if you're using Distillery or Elixir releases, or if you're just starting with IEX. It also can vary a lot depending on your deployment environment, right? Like if you're deploying to AWS, if you're deploying to bare metal, if you're using Docker. There's a bunch of articles out there that'll tell you or help you figure out how to get a remote console on your machines. But we're going to continue assuming that you can get a console to your machines. So once you have a console on your machines, the Beam comes with a bunch of tools that can help us out. The first thing's the sys module. We're not going to go into this too much, but there's some really helpful functions in there. What we are going to talk about is Erlang trace and Erlang trace pattern, as well as the debug module. So let's look at Erlang trace. This is kind of the building block for all of the other tracing tools built into the Beam. And everything else kind of stems from this. It's not the most easy to use interface, but it's powerful. And that's the reason everything's built off of it. Now, the first thing you have to address with Erlang trace is you need a tracing process. You need a process where all the trace messages get sent that handle them somehow. We're going to build a really naive one. This is just a simple process that starts, it has a start function that spawns the loop function, which receives a message, IO inspects it, and loops. This is not safe. This is not good. Don't use it in production. But it serves as an example of the types of thing that a tracing process has to do. It has to receive these trace messages and do something with them. And Erlang trace doesn't give you anything to handle that out of the box. So let's look at tracing everything that happens in a process with Erlang trace function. First, we need a process to trace. So again, a real naive example, we have this echo server. It spawns this loop function, which receives a message. The message is a tuple. The first argument is a PID and then a message. And it just takes the message and sends it back to the PID where it came from. We have a call function that it's like a little helper. You give it the PID for the echo server. It takes the message, sends it to the echo server, and waits for the response. Nothing really fancy there. So to trace something, right, we need the thing to trace. So we start our echo server, we get the PID, we start the tracer process, we get the PID for that. And then we call Erlang trace. We give it the PID of the process that we want to trace. The next argument is true to tell it that we want to start tracing. And then we have some options here. There's a bunch of them. We'll talk about a few of them. But this first one all gives you like a good sane set of defaults. And then this tuple, the atom tracer, and then that PID that we just got tells it where to send the trace messages. So then we call echo call and it sends a message to our trace server and responds. We get these nice 4 traces here. They all start with trace TS, which means it's a trace with a timestamp. PID is, these PIDs are the process where the trace occurred. You can see that this is the same as the echo PID that we started. We get trace events. The in and the out, the first and last ones, are scheduler events. So it's saying like this process was scheduled in. And then receive and send are receive and send. Each of those events has some details. For the scheduler events, it shows you what function's running when the process is scheduled in and out. And for the receive and send, it shows the process where the message came from and the process where it's sending it to. This next argument, I have no idea what it is. I couldn't find anything in the documentation that clearly said what it was. It's often the number 3. Honestly, don't know. If anyone knows, please let me know. And this last bit is an Erlang timestamp. It's measured in megaseconds, seconds, and microseconds. Now, that doesn't tell me much. I guess it could be useful to compare the microseconds relatively, right? If you had a few receives that happened over the course of a trace, you could compare them to each other. But other than that, it's not terribly readable to me. And like I mentioned, there's a bunch of options for Erlang trace. This is the documentation for them, not even the explanation of all of them, just the list of all the options. Erlang trace itself takes a PID, a port, or a spec. Then there's this second argument is how. Don't know why it's called how, but it's true if you want to start tracing or false if you want to stop. And then the flag lists. Some of the useful ones I'll highlight here. We have send and receive, which will show you sends and receives. You have calls, it'll show you function calls. Running is the scheduler stuff, the in and out. You can also trace garbage collection events. So this can give you a good idea of like what's happening over the lifetime of a process. You can also trace function calls, which I think when you're dealing with this kind of situation, like the one I mentioned at the beginning, where you're trying to find out what's happening for like a specific user or something, tracing a function can be the best way to go about it. We still have to start our tracer PID. And then we tell Erlang trace, instead of passing it a PID that we want to look at, we pass it the atom all. And that means it'll trace all processes that currently exist in the system, as well as all new processes. True to start tracing. And then we pass it the argument call, because we want to trace function calls, and the tracer PID, just like before. Now we have to call Erlang trace pattern to tell it what function we want to trace, right? It takes a tuple, module, function, arity, and then the argument true to trace all calls. And now when we call, since we're tracing string down case, when we call string down case, we get the result, but then we also get this trace. It shows that it's a trace. It shows the PID where it happened, which is the PID of my shell in this case. Call because it's a function call, and then a module function and the argument it was called with. And then we have to stop it, right? So we call Erlang trace all false, and that tells it to stop tracing. And now when we call string down case, it doesn't return the traces. And this is really important when you're dealing with production systems, because you don't want it to keep tracing all calls forever. You also don't want it to like start dumping out extra information after you found the information that you want. It could have performance implications and just be less useful if it's just flooding your terminal with information, right? So this is great. You can trace a function, but can we get more specific, right? Like in that example at the beginning, I just want to see what happens when my boss's user calls a certain function, because I know that he's the one with the problem. And yes, we can. There's this great thing called match specs. I'll show you how to use them, and then we'll talk a little bit more about what they are. So again, we start our tracer PID. We tell it that we want to trace all calls. And then now we have to generate a match spec. And there's a function in the debug module, debug.fun2ms. You may have seen something similar if you dealt with ets a lot. There's an ets fun2ms. But it takes a function or something that looks very similar to a function and generates this data structure. You could generate the data structure by hand, but they're like, even for this very simple example, it's kind of nasty to look at the data structure. And the more complicated you get, the harder it would be to do by hand. So this helper function is great. For this one, for example, takes a function with one argument s, and when s equals the string hi, return trace. And we're going to talk about return trace in a second. And then I'm just setting the same data structure to a variable, and you'll notice return trace in the last bit is kind of different. When I created the function, I just passed it an atom, and it gave me back an atom wrapped in a list. In order for return trace to work properly, it needs to be an atom in a single element tuple wrapped in a list. Now what return trace does, and this is very important, not only does it show you the call, when you call the function, it shows you the result, which can be incredibly useful when debugging systems, right? I want to know, like, this function that's supposed to send the OS notification to my boss, I saw it was called, but did it do anything? Did it return like an error struct or something? What happened there? So I need the return as well. We're going to talk a little bit more about the return trace thing in a second and why we have to do this little song and dance. But basically, I just generated that match spec, and then I pasted it and I wrapped it in a tuple. And then we call Erlang trace pattern like before. We give it the module function arity and then a match spec for the next argument. Now, since before, when I generated the match spec, I'm matching on functions that take hi as the first argument. So when I call string down case with foo, we don't get any traces as expected. Now, when I call string down case with hi, we get the trace for the call, right? It shows that string down case was called with hi. We also get the trace return from trace that shows the module function arity and the result. That's great. So the match spec, right? You could do something like this. This would take a function with one argument where the first argument is a user ID. It looks kind of like a function. You just can't like paste any function, especially with function bodies in there, but it looks a lot like a function and with guards. You can use most guards that you can use elsewhere. You can also use variables from outside the guard. So I could do like function with one argument s when s is equals UUID, and UUID could be a variable. You can't do that with guards normally. But dealing with the function body is kind of hard in Elixir, and we'll look at why that is a problem. So we've got an Erlang console and an Elixir console side by side here. On the left, we're calling debug fun2ms. It's a different match spec here, but we're taking a function that takes two arguments, where the second argument, n, is greater than 3, and we want to return the trace. And you'll see it generates this data structure. In Elixir, we call debug fun2ms with a function that takes two arguments. When the second argument, n, is greater than 3, return trace, except you get a compiler error. Undefined function return trace. It's because the Elixir compiler sees that return trace function and tries to look it up and use it, and it doesn't exist. It's not a real function. So like I said before, you can like return trace as an atom, and then it returns this data structure, and then you can manipulate it by hand in the console. Or if you're doing this a lot, there's a great library, EX2MS. I think it's started by Eric Meadows Johnson. And it was originally developed for the ets fun2ms, but it works with the debug module too. And it it handles generating the match specs from Elixir function code a lot better than the debug module one does. And the nice thing is, like I said, that it's just a data structure. You don't need EX2MS installed on the machine where you're debugging. You could have it on another project locally, generate the match spec you want, and just copy that data structure over to the machine where you're actually debugging. So you don't necessarily need it installed on everything. So that was the Erlang trace function. Now, there's another module I mentioned, the debug module, which is a wrapper around Erlang trace, and it handles some of the problems. You don't have to build that trace process. It gives you one, which is a lot more robust. It's about 150 lines of Erlang instead of like 3 lines of Elixir in the one that I had for an example. It also supports tracing on other nodes, which is kind of interesting. So let's see how you do the same type of operation there. To trace a process, you start the process that you want to trace, and then you call debug.tracer. That starts the tracer process where all the trace messages get sent. You don't need to keep track of the PID here though. And then you call debug P for process, give it the PID of the process you want to trace. And this all gives you like a standard set of things to trace for. And then when we call echo call, we get a very similar trace. It's formatted a little differently. We get the process where it happened in the first thing instead of in the middle. And then we get in and out for the scheduling, and we get the double left arrows for the receive and the bang on the line 3 for the send. And then we get the timestamp in Erlang timestamp format. It's all the same information, just formatted a little bit differently. And then we need to also stop the tracer process. So we call debug stop clear. You can trace a function. You call debug.tracer to start the trace process, debug P, and instead of passing it a PID to trace, you pass it the atom all. That tells it it's tracing all processes. And then you call debug TPL, which I can only guess stands for tuple. And you give it a module, a function, and then options. In this case, we're using the atom X, which I'll talk about in a second. And then we call string downcase like before. We get the same types of traces. Now notice, since I didn't give it an arity, I gave it that option X. It traces it for all arities, and downcase is actually has two different arities, a single arity and a double arity. And the first, the one argument version calls the 2 argument version. So when we call string downcase with hi, we see the call that calls the 2 arity version, and then the return from both. And then we also still have to stop clear the debugger. These 2 options, I think the .c on the debug.p is for calls, and the atom X on the debug.tpl has like a kind of standard set of options, but it also does the return trace, and that's kind of the important part. The third argument to debug.tpl, instead of being the atom X, could be a match spec. So we can still use the same match specs as before. Now there's some pitfalls for Erlang trace and debug. The interfaces are kind of confusing. With Erlang trace, we have to build that tracer process, and building a safe one is not something trivial you want to be doing, in the heat of debugging some production issue. You could potentially dump unbounded amounts of information, right? It doesn't stop tracing until you tell it to stop tracing. So if you trace a hot function, it could be sending tons of messages back to your console. There's also, I think, an ability to deadlock. For example, if you were tracing like IOInspect and you wrote a tracer process that used IOInspect, when you called something that called IOInspect, it would call your tracer process, which would call IOInspect, which would send a trace to your tracer process, and you get the idea. Now, there's a solution to this, I guess, in the form of another library that's not included in the Beam, but is incredibly helpful. And that's the Recon library, which is also an Erlang trace wrapper by Freddie Bear. It's production safe, battle tested, and much easier to use also. It has a tracer process, but that links to your shell, the group leader for your shell. And there's a formatter that links to the tracer. And if anything goes wrong, if you close the console, if you have a network outage and you get disconnected from the console, it'll shut down all the tracing processes and everything gets cleaned up safely. It also forces you to enforce the number of traces that you'll collect. So you're not dumping tons and tons and tons of traces to your console if you trace a hot function. One caveat is that it only works on a single node, but it's still super useful. So let's look at tracing a function, which is where I find this the most useful. This is all you have to do to set up the trace. You call recon trace, calls, you give it the module and the function, and then you just give it the atom return trace. And it's just the atom return trace. It works perfectly fine in Elixir. And then the second argument is the number of traces that you want to receive. One thing to note about this is I think it's determining the number of traces by just calling like function invocations in a process somewhere. So for return trace, you get one trace for the call and one trace for the return. So you essentially have to set that number to like double the number of calls you want to trace. It's just something to keep in mind. But once you have it set up with the single line, yeah, like I mentioned, it takes the return trace and you limit the number of calls. So once you have it set up, when we do string down case, we get the result. Now you'll notice the timestamp is in a readable format now. Yay. And it shows the PID where it happened, and then the module function and the argument, and then also the response. And then you'll see this last line, recon tracer rate limit tripped. That means it hit those two invocations and it's done tracing. Everything's cleaned up now. We don't have to worry about it continuing to run, causing any extra load on the system or giving you extra logs that are useless or anything like that. So recon is really the kind of punchline to this talk. Is you should check this library out. I install it in all my projects. It has no runtime overhead unless you're using it, so it can't hurt to have it. And when you need it, it's really helpful. But there's a couple other things that the Beam has and offers for tracing that I just wanted to mention. Oh, sorry, back to Recon. You can still use match specs as the third argument, or a PID. You can send in a PID as the third argument, and it'll trace everything that happens in a single process. So yeah, like I was saying, there's other things the Beam has built in that can be useful for tracing that I haven't quite dug into yet, but are kind of piqued my interest. There's the sequential trace module. And what I gather is it allows you to set up tracing where once you call a process that's being traced, if that process calls other processes, you'll also receive the traces from those and so on and so forth downstream. So you can see how calls cascade through your system. That sounds really useful. Also, I'd be interested in production safe debugging across nodes. So like I said, Recon only works on one node. It would be cool to build a system that worked on multiple nodes, because sometimes you're maybe debugging something behind a load balancer and you connect to a single node, but you don't know which node's going to get the call that triggers the action that you're tracing for. So being able to trace on other nodes could be really useful. And imagine doing it safely is really difficult because you have to account for, you don't want it to like clean up the tracer if you net split or something. And also there might be additional load from having to send the trace messages over the network. And like I said at the beginning, the sys module also has some helpful utilities like sys.getState that can be really helpful when you're debugging these kind of things. I have a list of resources, links to articles and documentation about this. The slides will be up on my GitHub, so you can come check these out. There's the first article is about getting your remote shell started in case you need to know how to do that, and also some other tools like Observer CLI that can be really helpful when you're dealing with tracking down issues on production systems. And with that, I'm about done. So thanks for joining me. And I think I've got a little bit of time if there's any questions.